I want to have a stab at creating a file to demonstrate what they call the chaos game. And I did a video with Numberphile back on this in 2017. The way I made the file that I used, the Geogebra file I used in that video, I don't think I would make it like that anymore. I feel like there's a simpler way, and I want to try and do that really quickly in this video. There is some more to explore, but let's get the basic bit done first. So as ever, I'm working on Geogebra Classic 5. Here is my window. For this, actually, I don't want to use the grid or the axes, so I'm just going to turn them off. There's always a quick way to do that in this little drop down menu here. You can always right click on the graphics properties, pop this up, and you can turn on show axes. There it is, and you can show the grid here, and that's useful to know anyway. But for now, I just think I'm going to start with just 3 points, A, B, and C, and these are the points that we use for the game. If you know anything about the game, then this bit will be familiar. If you don't, let me just quickly remind you. The idea is that you have a fourth point, starting point on the screen somewhere. Let's make a point D. And you do an iteration where you make D move towards one of those 3 points randomly. You can pick them at random, roll a D6. 1 and 2 goes to A, 3 and 4 goes to B, 5 and 6 go to C. That would be one way to do it. And crucially, you let D go halfway towards the target point that you pick. There are several variables here that have gone unstated. One is how many points do we use? We're using 3 here. The other one is how far do you move? We're moving halfway here. Let's change them later on. Let's just get this working first of all. And we can do this really easily. The idea being that I could use a way of animating in Geogebra to just repeatedly iterate that. Now, this is worth demoing carefully because there's no obvious way to do like a for next loop, which is familiar, I hope, to anyone doing any coding out there. But in Geogebra, there's no obvious way to do a loop until you realize you can use a script on a thing that updates all the time. And if that thing updates all the time, every time it updates, it should run the onUpdate script. And that way you can get a continuous construction to be repeated. So that's what we're going to do. The way I'm going to do, basically, I'm going to make 3 vectors which will update wherever D is. There's a vector to go from D to A and D to B and D to C. So I'm actually going to make a list of them. We're going to call it vec list, and lists need curly braces. Let's just make the vector from D to A, then the vector from D to B, and then the vector D to C. And you can see them visually turning up on the screen. Actually, you don't really need to be able to see them. I just need to be able to have them in there. So I'm going to turn them off there. And that's what I'm going to choose a random vector from that list in order to know which way to go. I think previously I implemented it by rolling a d6, if you like, but you can get random numbers in Geogebra quite easily. And then if it was 1 or 2, go to A, or D3 would be, if it was 1, go to A, if it was 2, go to B, if it was 3, go to C. But this is, I can just pick a random element from that list, and that list is always updating. Those vectors are moving around. So let's just turn them invisible for a moment, and I'm going to put the whole command in the scripting function here. So actually, this is the crucial thing. Let's make a slider that will be our constantly changing thing. I'm going to call it T for time, if you like, but I'm actually going to hide it in the main thing, and it doesn't really matter what it goes from in between. What I want to know is it's updating quite quickly, so I'm going to make the increment small. And another important property of this will be its speed, which we're going to go and change later on. But at the moment, it doesn't do anything. In its properties, though, in the scripting tab, we have an onUpdate, and that means anytime that slider updates, it should run the commands in here. So if I make that slider animate, it's just going to continuously run the commands in here every time the animation forces it to change. So every time that does happen, what I want to do is set value of D, the point that's in the middle, and I want to change that to be D plus one of those vectors. So let's choose one of those vectors. I'm going to say random element. Let's close all that. Random element from, what do I call it? Vec list. So it's just going to pick one of those vectors. So I'm just going to do D plus that, but I don't want it to go the whole way. I want it to go halfway. That's it. And now if I move T around, you can see D is just trotting around. So there's only 2 things left to do. One is to animate T, which I can do very easily by right-clicking it, and the other one is to make D leave a trace, and then let's animate T. We are playing the chaos game. We pick a random point, we go towards it. Now, this is already doing the main thing. The rest of it is just dealing with the speed issues, and this is the sort of file I demonstrated in the Numberphile video. it's already pleasing that this is doing a pattern which maybe you didn't expect. Let's just make it happen a bit quicker, because the speed of this is going to control how quickly those things. So let's just make this go as quick as it can. I'm just going to crank up that speed. And we should see now T is moving quicker. It doesn't really matter what T is doing. It's just the fact that it's updating, so I can hide it. And now we just see D chugging its way around the screen. And you are seeing the shape of a Sierpinski gasket. Actually, not quite. This is not an equilateral triangle. There were just 3 points I put randomly on the screen, A, B, and C. And if I started this again, I can Control F to refresh and just move point C over here. Let's just do a new version. Oh, what happened there? Let's move. I need to get the arrow tool. Move point C up here. Let's refresh it there. And you'll see that we'll get a skewed version of the triangle. So it's already updating. I like this about GeoGebra in that we've got these draggable points. And although the trace function is just leaving a sort of mess on there, and it'll have the old one out, if we clear it and drag one of the points around, we get a new fractal drawing occurring. So this is dead simple. There was one command in the update script for a slider, and it just off it goes. And that's actually a really important principle in working with GeoGebra. If you want something to repeat on a cycle, like you might do in a loop in a coding language, having a slider with something in its onUpdate script is a way of doing it. It has some weird artifacts when you do it like that, but it's the way of making this happen, and you can see that this is dead easy to make. We have done it in a few minutes. There's a few things to maybe improve. It would be nice to keep track of how many times it's done it. So while you're enjoying that, let's upgrade a few things. Let's make a variable called I for the index. I'm going to set it to 0. And that's just going to be a number I change. In fact, what I can do is leave this on the screen as a little indicator. And all I can do is change the T script there. Let's stop the animation for now. Change the scripting that had the crucial command in, just to say set value I to be I plus 1. And that's an increment way. So every time that script gets run, it's going to increase I by 1. Let's just check whether that works. I need to animate T. There we go. And it's just counting how many times it's doing it. A couple of other things that would be really useful to do here is have a reset button so it clears it. Let's discuss that, and maybe a start and stop button. So first of all, let's have a button. It's going to be a reset button, and I think to reset this, what I'm going to do is start animation of T false, so it stops the animation. That start animation command takes a true or false argument there, and let's set the counter I back to 0. And that should clear it. And maybe I wanted to clear the screen as well. I'll do that. So I'll do zoom in 1. That means literally zoom in precisely where we're at now, but it does force the trace to disappear. So it's a neat way of clearing the trace off a screen. And this button will reset it. It should stop the animation as well. Yeah, be helpful if I was on the arrow tool just to avoid making a new button here. Anyway, that's reset it and it stopped everything. So it'd be good to have a way of starting it again. I'm going to do that with a checkbox so we can turn it on and off without resetting. Let's call it animate. A checkbox is normally used to hide and show objects. I'm not going to use it for that though, so I didn't select anything to hide or show, but I'm going to change the script of another bit of scripting. When you update the checkbox, i.e. by ticking it or unticking it, I want to start animation or stop it. So start animation of T, and I want it to depend on what the checkbox is doing. So the checkbox is called A, so I want it just to take the value from A. If A is ticked, then do it, and if it's unticked now, it will not do it. It will stop the animation. And I think that's all I need it to do. Let's have a look. That's animating. That stopped animating. Animating. Stopped animating. Reset. Nice. One thing I should notice, if I click reset, it doesn't untick the box. Let's just change the script to tidy that up. So on click for the button. You can see the on click scripting is a different button. If you have a button, you have an on click scripting option there as well. So let's add another one, which is set value of A, which is my Boolean value, to be false. So it does untick itself. I think we want it to do that. Let's just check reset, unticked it, animate, reset, animate, stop animate, animate. Lovely. That's how I made the chaos game thing. So there are a few other things we could do. We could play with the couple of variables I talked about. We could play with how many points, and we could play with proportion you move towards one of those points. So that's the first half of the video down. Let's look at playing with those things in the next bit. Okay, so time to upgrade this file. Before we do anything else, maybe just make it more aesthetically appealing. So I'm going to just refresh the thing. Let's reset it properly. this dot, the size of this dot is what's leaving the trace. So if I make that dot tiny in the style, and maybe make sure it's a filled dot, this is going to take a lot longer to do anything, but maybe we'll get a finer resolution. And so maybe I'll just talk for a bit about this while it's chugging away, but we'll get a more detailed looking, less blotchy looking plot. It would be nice if it went even quicker. To be honest, though, I think if I change the properties of T and just crank up the speed, I can do that, where it's in the slider properties. There we go. I don't think it's going to get any quicker. You seem to very quickly hit a limit of how Geogebra handles it in the processing, and it's just not going any quicker. If you find a way of better controlling how the speed of a loop in Geogebra, then I'd love to hear it, because that sort of feels like an arbitrary bit. And I've said it in other videos, but a reminder of how that speed box works. I think the number in there is roughly... speed 1 indicates that it'll do a complete slider from end to end in 10 seconds. So it's kind of like out by a factor of 10 if you're measuring seconds. If it said 10, it would be measuring the time it takes to complete, but it's only saying 1. So divide the number, multiply the number in that box by 10, and you have the number of seconds. No, that's not right. I think it's backwards, isn't it? So a speed of 10 is going to be 10 times quicker. So is it 1 over... Let me sort this out. Doing this on camera is probably not very wise, but if I set this to speed 1, it takes 10 seconds, and let's make T visible. It takes 10 seconds. 3, 4, 5, 6, 7, 8, 9, 10 to get from end to end. And I've just justified that. It's the first time I've actually probably counted that. Very accurate counting in seconds. I have no idea, roughly speaking. But if you make it speed 2, it will take... about 5 seconds. It's twice as quick. So what's that? So doing this on camera is hilarious. That number, 1 over that number times 10. Is that right? So 1 over 2 times 10 is 5. And if we put a 10 in there, it should take 1 second to go. 1, 2, 3. So 1 over that number times 10. I think that's what the speed box does. The reason I'm going on about it is that if you wanted to make a slider to control the speed, you could. You just make a new slider and put that name of that slider in the speed box. I'm not going to bother. I just want it to go as quick as I can. And the reason I've talked so long arbitrarily about that thing is that it has now made a nicer, higher resolution looking version of a Sierpinski gasket with these 3 dots. I would like to do 2 things. One is control the number of dots, maybe like 4 dots, 5 dots. Let's have a slider for the number of dots, for goodness sake. And also maybe let's control the proportion it goes to other places. So let's reset this and stop it. And let's get some more points on the screen. I'm going to manually put them on so that they're completely draggable. These are not procedurally generated. The numbering system is now slightly out of order. Let's fix that. So A, B, C. They're not numbering. Did I even go in a different order? E, F, G. Let's drag the label instead of the point there. H. And in time, maybe I'll want to turn off. And D is my start point. That's really tiny. Oh, it's leaving a trace. That's not what we wanted. Okay. These are now random points on the screen. What I'm going to do is make a list of these points. We're only going to go up to 7 points for this. You could probably go more, but because I'm doing each point manually, I'm not going to bother. Let's make a list of those points. So it's A. I'm using control to select things. I'm not going to select D because that was my start point. I should probably rename it, but I'm not going to bother. Selecting them in order. And if you drag selections from the algebra window into the input bar, it makes a list of them. And that is one of the biggest shortcuts I've found rather than having to type it out. Let's make that a list of points. I'm going to call it point list, PT list. And there it is. And what's good about this is now I've got a list in order. I could make a slider that controls how many of them to choose. So let's make a slider called N. By the way, you can click integer in the slider creation thing. All it does is change from 1 to 30 by default and it go up by 1. You can just do a number and go from 1 to whatever you want. In this case, I want to go to 7. I think that's the maximum of points, and go up in 1s. Same thing. I do want to call it N though. And I would like to make another point list, maybe a selected point list. That's called an S point list, which is the first from point list, but the first N elements. It's only going to pick one of them, but N is one of them, and now you can see that dragging that up makes that list longer. So I could hide all these points. I wonder if I'm going to be able to see them. Yeah, there they go. The trouble is that these green ones, which are generated by the list, are not draggable. So I probably we'll have to do a little bit more manual searching to... Yeah, I'm going to have to change the properties of these blue points. I'm going to hide these. So HG. And I just want them to be visible or invisible based on that. And I also don't want them to be less than 3. Otherwise, we won't get a shape. So let's just let this go down to 3. I'm just showing you the principle here. So A, B, and C are always going to be visible. Let's make E. I'm going to change the properties of E. In advance, there's a condition to show the object. And I'm going to change that condition to be when n is greater than or equal to 4. Because E is the 4th point. Disappeared at the moment. Okay, let's keep going. So then it's quite useful to be able to go in the list here. So this is fn greater than or equal to 5, g n greater than or equal to 6, and h greater than or equal to 7. That, I think, is working. Yes, they appear. And they're still draggable, which is nice. So I just need to make my random vector list go between any of those points as well. So my vector list was defined by hand. Let's do a slightly better way of defining that list. So I'm gonna redefine vector list. I'm gonna delete it. I better not make it animate because it will probably have a fit because vector list doesn't exist. So let's redefine it before anything happens. It's gonna be, I'm gonna use the zip command like almost every time. So I want to run through the list of points that we've chosen. So it's the S point list. No. That's where I want to get them. I want to get the vectors. So let's do a vector from, always from D to some point, which I'm going to get from the list of points I want to use. So let's let X point come from S point list. And that's it. And that should give us a list of the vectors. There we go. And as I change the slider, it only gives me the ones I need. Nice. Okay, so now vec list is updating depending on n. One other thing I was gonna let's just check it's working. I don't want to see the vectors. Let's see, we're at 5. Let's change the So the annoying thing about this scripting thing, I said there were some artifacts that the crucial commands are buried in the scripting page of a slider which might be invisible, and that's a painful way of programming, if you ask me. But it works, and Geogebra has lots of other advantages, so that's what we're talking about here. So it's just going to set D to be D plus half of a random element from veclist, and since we've just updated veclist, that's still going to work. This half I would like to be something better, so let's make a slider which controls that proportion. And I just call it prop. Between 0 and 1, I just got to get this the right way around. If I go halfway, it's symmetrical. If I wanted to go a third of the way, then it is just a third of that vector, isn't it? So, yeah, okay, let's try that. Now let's change back in the scripting of T. Instead of a half, let's put prop times random element. And that's it. I think that's all updated now. Let's leave it as a half and see what happens. Let's check it works on 3 points still. So n goes to 3, and we animate. And it's doing that tiny little diagram there because my triangle is really small. But let's reset that and crank n up to 5, and it should just automatically work for a 5-point thing. Now, I know that having a proportion of a half here is not going to look particularly spectacular, but let's just try it. It does look like it's filling the space between the 5 points. And there's a reason why the proportion of half is not going to do anything particularly nice, although this is where you get to experiment. So I know from playing around with this that if I do, say, 4 points, and maybe I'll make them into a squarey shape. Although the nice thing, it doesn't have to be exact for this to function. And we'll go 2/3 of the way, roughly. Let's go about 70% of the way, and let's see what happens this time. So D is a really tiny point, so it's going to take a while for this to build up. But what I hope you will begin to see is that we are going to create a fractal representation of the original corners. Now, just cast your mind back. When we had 3 points, we made a triangle shape. And actually what you are seeing was 3 triangular copies of the original shape in the 3 corners. And then they touched together because of each triangle being half the length made it fit together. So if you have 4 points, actually what we're creating by this iteration, and you can go and think about this, it's one of those things that when you first time you see it feels like utter magic. It's just utterly astounding. And then the longer you think about it, it does genuinely, like a lot of maths, become, oh, well, of course it's going to do that. Which is a strange transition to go from something which is almost unbelievable to something which feels like, well, of course. A lot of maths feels like that. What's the quote? Maths is the art of making the taking the very confusing and making it blindingly obvious. No, that's not the quote. You can quote me on that if you want. I think there's a Douglas Adams quote buried in my mind somewhere. Douglas Adams quotes Isaac Newton as genius because he rendered the hitherto non-existent blindingly obvious. And we're not talking about gravity, we're talking about his invention of the cat flap. I think this is a quote from Dirk Gently's Holistic Detective Agency. Right, go and look that up if you care. What you can see here is I've created 4 sort of like this trapezium shape. That's English trapezium. Go and look up the difference between American trapezoid and English trapezium if you care. That's repeated like in this shape here. And in each of the 4 copies. So actually, this is always going to create a fractal thing, and the balance between the number of dots and the proportion of the distance you go is going to be quite important. So it's working, and I'm pleased about that. Let's reset it, and maybe let's try making more of a square shape. If you do want to actually lock it to square, you could turn the grid points back on, and it will lock to points if you want to. If you don't want it locking to points, by the way, it's in here. This snap to grid option is buried in this menu here. Sometimes that's quite hard to find. Is that a square? I think it is. I'm going to start D at point B and let this go just over halfway. I wonder, I'm still feeling my way slightly. Let's just see what 0.54 of a proportion goes. Okay, here we go. I'm going to turn the grid off. Oh, that reset the trace. You see how I think I used the word ephemeral before, how ephemeral that trace is. Now it looks like we're kind of filling in the whole grid square here, which the nice thing about the original one where you go halfway and you've got 3 points is that you get that gap in the middle, which it never goes into unless it's the first few iterations. And that's what feels slightly magic. Here you begin to see a cross in the middle. And that's pleasing. If I'd set this to be exactly a half, by the way, that cross would be width 0, and actually it would be filling the entire square, and it doesn't look very interesting, although it's a fractal copy of itself still. Here what you're seeing is the big square we started with copied into the top right. What's that? Top right for you, top left, bottom right. I have no idea if I've said those in the right directions. It's creating a copy of the whole thing, and each of those has copies of the whole things, and it's just doing that all the way down in a sort of iterative way. And you can see, I think, that the sort of these runways in the middle, that cross shape, but then the cross shape is repeated in this square, and if we went long enough, it would be repeated in that little square in there. What's weird is that here, if you follow that reasoning all the way down, the point is not allowed to land anywhere. Like, it's all white space, even though actually here it looks kind of full. And that's the same with the triangle version. This is where fractals get a bit confusing. Or obviously we're not seeing fractals, we're seeing approximated fractals. And in fact, it's never, this D point is never actually getting into the zone it has to be in. It's just getting closer and closer to the attracting points, which is a fractal set at the deep thing. Anyway, the point is really not here about the maths. This is how to build the thing. And I already like the fact that this has been built with one line in a scripting command, and we've now got a variable number of points and a variable proportion. And I did a little bit of talk about that in the Numberphile thing. There might be more to do with this, which we should save for the last part of this video. Okay, I let that video just run a bit speeded up so you could see the end result and that somewhat random fractal structure we got because I picked a random proportion. Despite having just said that this video is not really about the maths, I want to talk a bit about the maths because I only really thought about the maths again recently, having made this video and reconstructed it, and I realised some nice things about the things we've constructed, particularly about fractal dimensions and being able to create the fractals that you want to create and knowing some more properties of them. So let's backtrack a little bit. I'm back on the file we made in the earlier part. With the upgrade, we can change the number of points and we can change the proportion you move. Let's make an actual triangle, equilateral triangle. To do that, I'm going to make sure I can get those points in the right places. You can always change the properties of the grid. In this case, I'm going to make it an isometric grid and turn it on. So now I can snap the points to some nice 60-degree things. So we can make a proper triangle shape. I'm actually going to put the starting point D on one of the points so I know that I'm in the pattern already. We can zoom in a bit, I think. They're locked in place now. The snap to grid is on. We can turn the grid off and we're just going to run this and we will see hopefully a nice equilateral triangle version of the Sierpinski gasket, Sierpinski triangle, Sierpinski sieve, whatever you want to call it. And I want to use this as an example to talk about how we know what sort of dimension this fractal has. If you haven't thought about this before, this is where the word fractal comes from. This object we're creating is on a two-dimensional surface. That's kind of the flatness of it. But it's got lots of holes. In fact, if you think about the object, and particularly as you see it happening now, like it's got a hole in the middle, and then each of the triangles left has a hole in the middle of that, and each of the triangles left there has a hole in the middle of that. It's holes all the way down in the mathematical ideal of it. So there's no substance to it at all, in which case it's not really feeling like it's covering an area. In fact, it has zero area. But it also doesn't feel like a line. And that's the intuitive way of describing why this feels like it has a dimension between 1, which is a line, and 2, which is a plane. It feels like it has a dimension between that, which maybe you'd call a fractional dimension. It's not quite true. Fractions can be whole numbers, or but if the phrase fractional dimension sounds like it's too long, it's because it gets shortened to fractal dimension, and that's where the word fractal comes from. And that's the responsibility of Mandelbrot and a bunch of others in the late 20th century. That's where the word has come from, fractional dimension. The dimension of this object feels like it should be between 1 and 2, and we can actually put a number on that to make more sense of it. So you can see this thing is chugging away nicely and building a nice proper fractal for us, the Sierpinski gasket. So what dimension does it have? And to sort this out, we're going to need to go and look at a bit of actual maths. So I'm going to flip over to OneNote and draw you some pictures. If I try and draw the triangle that we've just been seeing, I've left it running in the background. I'll just try and draw this, and actually it's not going to be a great drawing. I like the idea that maths is the art of reasoning from bad drawings. Hat tip to Ben Orlin, who has a Twitter account and written books, the maths with bad drawings. Excellent stuff. But I really like that quote. I need to find out where that quote is from. I'm not actually sure. Maybe I made it up. But the art of reasoning from bad drawings captures the idea that you have to draw accurately and precisely to be able to reason accurately and precisely from them. Anyway, we're going to try that. So I'm going to draw the Sierpinski gasket. I might speed this up because I want to draw enough of it to get a handle on it. Okay, that took longer than I wanted it to take. There's probably a better way, but the nice thing about doing something the long way by hand is that you do get a feel for how it scales, and actually drawing the third level of that takes longer than it feels like it should, and you get a feeling for how many copies you're creating by doing it the hard way. The point I'm trying to make here is that when I want to think about this object, the reason I recognize it as a fractal or sort of self-similar thing is I can see kind of a copy of itself in itself. So the whole thing is actually captured in this little corner and in the other corners as well. And I hope that's kind of obvious. That's if the holes go all the way down, if this is repeated indefinitely. And that's the mathematical object I'm thinking about now. But that means we've got a way of capturing how it scales. Let me point out that this little version, this triangle in the corner here, gets used 2 other times. So there's 3 copies of it in the whole thing. But the whole thing is twice as big in its length scale factor. So if I write this down as 2 times bigger in length, and maybe I should write the word length. I'm talking about the length scale factor when I talk about times bigger. And how many copies? There are only 3 copies to make the full diagram. That's particularly because that middle triangle is not there anymore. That doesn't seem that unusual until you think about how more traditional shapes scale. So let me look at a couple of examples. Let's look at a square. And if I subdivide that into smaller squares, like this, you can see that the whole square has got a copy, do it the same style, down here. In fact, there are 4 copies. So we can do the same reasoning on this one. The length 2 times bigger to make the big square from the smaller square, and we need 4 copies of the smaller square to make that happen. And this carries on in a similar manner. If I have a square subdivided into 3 sections, like this face of a Rubik's Cube, say, then the length is 3 times bigger. I'm going to stop writing length very soon because it takes me a while. And how many copies? Well, we need 9. And I hope you recognize where these numbers are coming from. These relationships are because, in the top one here, 2 squared is 4. I know I'm patronizing you. 3 squared is 9. That's why those numbers are connecting. And that 2 is the crucial number. That's because we're looking at a 2-dimensional shape. Literally, that power of the length scale factor to make the area, or the sort of copies of it, is a clue to the dimension you're in. If you need 8 copies to make it twice as big, you're in a 3-dimensional space, but here in a 2-dimensional space, and so the power is 2. But what I just wrote down about the Sierpinski one is that the length is 2 times bigger and you only need 3 copies. So if I tried to write down the same relationship, it would be 2 to the power of something is now equaling 3. And it's rather obvious that that x is not 1, because 2 to the power 1 is 2, and 2 to the power 2, for example, is 4. We've seen that down here. So what is x? Well, we could solve that, but the point is it's not going to be a whole number. And that's our starting point for the idea of a fractional dimension. So let's actually solve that equation and find the actual dimension number we're talking about. Although it's, spoiler alert, it's going to be an irrational number. Let's do it down here. So I've got 2 to the x equals 3. Take logs of both sides, log of 2 to the x. I'm using natural logs here. You could use any base logarithm you like. That's the nice thing about log. So the power comes down, x log 2 equals log 3. And if you're not sure about logarithms, go and look that up. They're a really useful tool in this sort of calculation. Fundamental in this sort of calculation, actually. So we get log 3 over log 2. And I don't really want to simplify that anymore. I'll probably just reach for a calculator to get some sort of final answer on this. Let's do log of 3 divided by natural log of 2 and 1.5-ish, 1.584, 1.585. That is the dimension of the Sierpinski gasket. And it's somewhere living between one-dimensional space, i.e. lines, and two-dimensional space, which is planes, because it has properties of both. And that is why these things are weird. But the fact that you can put a number on this is where the whole beginning of fractal geometry works from. Now, it's not always as simple as this. If you go and read the Wikipedia page on fractal dimension, you will see very quickly. Wikipedia pages on maths are always quite opaque sometimes. But what I've calculated here is what they call the Hausdorff dimension for this shape. And with other more complicated fractals, it's much harder to get a handle on how it scales. But when they are this self-similar, you can get this argument quite quickly. And actually, the reason I'm talking about this at length is that you'll begin to realize that the 2 numbers I've used here are the number of copies in this shape and the scaling. And those 2 numbers are what are decided by the 2 variables we had in our Geogebra thing, which is why this is nice. So if we pop back to the Geogebra window now, and left this running, and you see it's really made a rather nice copy of the Sierpinski gasket. But let me point out the 2 numbers. The n equals 3 is these 3 points. Each of those target possible points that the thing gets dragged towards is basically creating a scaled copy of the entire diagram. So this is a bit self-referential, but whatever the diagram is, it's going to get scaled at half size, because the proportion is a half, with a center of enlargement at those 3 points. And that's why we get 3 copies of the whole diagram, one up there, one down here, and one down there. That's the clue to how all these things work. And as soon as you realize that, it's not like whatever the shape was going to fall into, it was going to have to be a shape which is repeated, self-similar copies of it at half size in the 3 corners. And that's the shape defined by this. So it gives you much better intuition about why this shape emerges. It's curious that the first time you see this, and myself included, it felt like absolute mathematical magic, just random process creating structure. And I still love that feeling, but like a lot of maths, the more you think about it, the more it becomes like, oh yeah, sometimes maths is the art of rendering the completely not obvious blindingly obvious. And sometimes when you understand something, that's what maths, the penny drop moment, feels like. But this gives us a handle on how to make other shapes. So, for example, just now I did one where I said n equals 4, so I'm going to ruin this lovely thing and let's stop it. And I think I set it to be 0.54. So let's have a look at that shape I made before. And what I'd like to do is calculate the fractal dimension of that, which is much less obvious because I didn't pick a neat proportion. But let's go back to the OneNote screen and calculate that one. So it looked something like this. I had my square and there was a sort of cross shape in the middle because I didn't... It filled in. So the whole copy of the whole thing has gone scaled to the 4 corners at a proportion. Actually, it's 1 minus 0.54. So I had n equals 4 and the proportion, I'm going to leave that as p, 0.54. That means this scale here was 0.46 and there was a little bit gap and that was another 0.46 on the other side. But then that was copied each one as well because it's got to be a scale copy of the whole thing. And so this is obviously a really bad drawing of the thing I had. But you saw it emerge at speed earlier. Oh, that was terrible. The point I'm trying to make is that each of them then has a copy as well. I'm not going to do the whole way around on this. Let's just do this one in the corner. It still takes me longer than I want it to take. But I can work out the fractal dimension of this object because I know the crucial things. I know that one copy of it here scales up. I can see there are 4 copies. The slightly not obvious thing is how much longer is that line? Well, I need to figure out how many of the original copies fit in there, and original copy is 0.46 and the whole thing is 1. So it's 1 over 0.46 times bigger. Let's get a number for that. We might as well. 1 over 0.46 is 2.17, and then the equation I need to solve is that number. So 1 over 0.46 it's just a bit bigger than 2, and that makes sense. It's just a bit more than 2 times longer there. To the power of something equals 4. So let's solve that. Going quickly, log 4 over log 1 over 0.46. I'll just do the calculation in full. Let's get the calculator back. We've got log of 4 divided by the log of, and I could do also simplification. I'm just going to type it in full here. We'll do some algebra on it in a minute. 1.78. So my dimension of this shape is sort of higher dimensional than the Sierpinski gasket. Maybe that makes sense. It's got less holes in it. Did I say 1.78? I think I did. Doesn't really. 1.785. Let's just go with that. I don't really care about the detail here. The point is, because of the 2 variables I have in the Geogebra, I can immediately calculate the dimension of the shapes. And in fact, let's just go back to the Geogebra file and make that calculation go in there. And hopefully, actually, let's do the algebra on it first. What I'm doing is always, it's going to be, the proportion it is bigger is 1 minus p. That's the scale of that bit. And the number of times bigger is 1 over that. So this number becomes 1 over 1 minus p, rather, that bit's there. And the number of copies is there. So what I'm solving each time, and let's just write this down nice and big, is 1 over 1 minus p to the power of x equals n. Let's solve the thing. X equals log n over log 1 over 1 minus p. And I could tidy this up. It's going to be log n. That's 1 minus p to the power of minus 1, so it's minus log 1 minus p. I don't know if that's easier to type in, but that is going to be the fractal dimension of whatever I make with the chaos game. And I can do that calculation dead quickly in Geogebra, so let's do that. Back in Geogebra, I've called p prop here. Never mind, let's just go with that. So let's call it fd for fractal dimension. It's going to be the natural log. How do I do natural log? I think it's just ln. Yeah, it recognizes that. Log of 4 divided by negative log of 1 minus prop. And what have I set up at the moment? So this should be the one I've just calculated. What, 1.7 something? 1.79, there we go. So fractal dimension, I can pop on there. Let's just make that fixed to the screen so it doesn't move around. Good. If I go back to the Sierpinski gasket, you can see that I've got 1.58. And so there's some curious outcomes here. So for example, when I have 4 points, and I leave the proportion out at half, it's claiming the fractal dimension is 2. It's claiming we get a 2-dimensional space. And actually, we do. If I turn the grid on again and I make it not isometric, that's probably going to be helpful here. Let's make it grid line again. And we just get our square back. And I leave it set up with the same proportion. It's got to be a square, and you'll see why in a moment. Let's put the starting point on one of them. Close enough, and animate that. You can see that the shape it's going to produce now is really not very interesting. It's, in fact, just a square. And let's just think about this. I've got 4 points, and that means I'm going to make 4 copies of the whole structure. And this time they're going to be half the size each time in each corner. And that is precisely the 4 squares. So there's going to be a square here. I wish I'd centered this on a corner instead of there. But there's a square here, a square here, a square here, and a square here. And they completely meet exactly. So it's just filling the space. And when I first did this, like, well, this is boring, and at least the fractal dimension is backing up saying this looks like a 2-dimensional thing. But here's the interesting thing. If you don't put them in a square, and I'm going to do that, I'm just going to put E sort of over there somewhere. In fact, yeah, I don't know what that's going to do. Let's clear it and run it now. Well, maybe I kind of know that if we make something a little bit more skewed, we're going to see something a little better. So let's do this. I haven't tried this in advance, so I don't know if this is a perfect thing, but I'm going to make it a sort of a kite shape. And let's just animate that. So this time, even though the fractal dimension hasn't changed, it is not going to fill in that entire kite shape. There's going to be some gaps. And I was curious about this. I didn't really understand it. But then once the structure started emerging here, I started to get this weird impression that I was looking at something which wasn't flat after all, despite it being on 2 dimensions and claiming to have a fractal dimension of 2. It looked like a 3-dimensional thing. And you can just about see it beginning to emerge now. It looks like there's a sort of triangle between A, B, and C. And you can just about see sort of, like, it looks like there's an edge there. And then something getting pulled up into a sort of triangle pyramid-y shape over there. And there are some gaps going on. Now, I appreciate this is really hard to get a handle on. But once that thought occurred to me, I was like, wait, this looks 3-dimensional. It suddenly occurred to me, and this is the reason I made this end of the video, is that this was new for me. I'm like, well, why don't I just do this in 3 dimensions? That point E doesn't have to be in the same plane as A, B, and C. and maybe you can predict what happens. But if I put them in a nice arrangement, the maths is exactly the same. I can go in a three-dimensional vector towards one of the points, but I will get a three-dimensional structure. So let's have a look at what happens with that. It's slightly against the spirit of this channel, but here's one I made earlier. It's the same setup. I've got O, B, A, and C as 3 points. I've put them in a tetrahedron. I've just done it on the 3D view. I've done some other bits on how to set up the 3D thing. Otherwise, it's exactly the same maths. It's just picking a point at random and going, this time, half of the way there, but we've got 4 points. And you can already see what is emerging here. This is not a two-dimensional structure. It's a three-dimensional one. But the same thing happened with 3 points in a proportion of a half. With 4 points in proportion of a half, if you let the 4 points have 3 dimensions about them, you get a tetrahedron version of the Sierpinski gasket. It's a Sierpinski tetrahedron, if you like. And it's really nice. I've sped up this video and cleaned up just so you can see this happening more quickly. But the nice thing in Geogebra about doing a trace on a point in 3 dimensions is that it doesn't disappear when you rotate it. Now, it does disappear if you zoom in or out. So careful with that one. It's still ephemeral, as the word I keep liking to use here. But the rotation means I can still see this in 3 dimensions, even though I'm looking on a 2-dimensional screen. And this was a big revelation for me that I can make a... Of course I can. I can make a 3-dimensional fractal just by using the same maths. The puzzle here is, though, that as we just talked about, the fractal dimension of this setup is apparently 2. And this is because this is, in some ways, a special fractal. The Sierpinski tetrahedron has a fractal dimension of 2, despite not existing in 3D space when you look at it like this. In fact, the 2-dimensional version has a fractal dimension 2, so this is kind of independent of how you actually look at it. Somehow the plot of set of points here has some sort of 2-dimensionality about it. It just happens to be a whole number, but it's not really like 2-dimensional flat things. It's looking more like a 3D structure or something embedded in 3D space. But there's a nice bit of consistency. If I go back to a file that's... I haven't polished this one up, and I can rotate this around. You can see that if I view it from a certain direction, so I can see the structure of it here, but I can also, if I view it from a direction which is parallel to 2 opposite edges, and there's a nice view from command. What's it called? Set view direction. Set view direction. And I've got a line that I've set up in the right direction, so it's the direction. Do that. It is a square. In fact, what we were seeing earlier when I had 4 points in a square is just the projection of that 3D tetrahedron onto a flat surface, and from the right angle, it just fills the square. So it does look like a 2-dimensional thing, and it's kind of nice that the fractal dimension is backing up from one point of view that this is just covering a square. Of course, now we understand this, we can do all sorts of things with some other fractals. Again, slightly out of the spirit of this channel, here's one I made earlier, but it's the same build again. This time I've got 8 points on the screen. Labeled O, A, B, C, D, E, F, G, and X is the point that gets moved around. And this time I've set it up so that they're on the boundaries of a square. This was a very deliberate design. I realized that I understood how the design gets made. I wanted to make whatever the pattern gets made, I wanted to make 8 copies of it, and with these points as the centers of enlargement of that. And if you think about that, what that will do, we need to know the proportion. To get them all to fit in, there are 3 along each side, so I need the scaled copies to be 1/3 the size, which means I need to move 2/3 towards the target point. And that's the 1 minus bit. That's slightly confusing. So I've set this up with n equals 8 and a proportion of 2/3. In practice, that means to get the thing 3 times bigger, you need 8 copies. And if you know anything about fractals, you know what fractal is about to emerge. But I'm going to run this, and I'll probably speed it up in time. So otherwise it's exactly the same build as we did before. But what you see emerging here is the Sierpinski carpet, which is like a square with imagine it divided into 9 squares, like a Rubik's Cube face or something, and you take out the center square. But all the squares you've got left, you also take out the center squares of them and go on all the way down. In fact, let's look at a speeded up version. And this Sierpinski carpet was a realization only because I knew about this sort of fractal, because I'd spent quite a long time helping build a 3-dimensional version of it called a Menga sponge with the Mega project. So this is 7 years ago, back in 2014, I think. people around the world, Matt Parker, Katie Steckles, and I all were working on a project with a lot of other people out of card, no glue, building Menga sponges. So a cube with the centers sort of drilled through leaves 20 cubes around it instead of the normal 27 to have a cube 3 times larger. But then each of those 20 cubes have holes, and it's a fractal like that. So I knew about that, and the side of one of those Menga sponges is a Sierpinski carpet, like we're seeing here, or a Menga carpet, some people call it. So it's a really nice fractal in its own right, but of course we should try the three-dimensional version, since we know the three-dimensional version even works in Geogebra. But to do that, we're going to need 20 points and have a scale of 2/3 to get that to work. And now I did try that, but there were some problems. So let's have a look at it quickly. You can see the 20 points here, and then 2/3 proportion, so you get a 1/3 size copy at each of those points. And this works okay. I had to run it a few times in Geogebra because it takes a long time to fill this space. We need to get lots of points to make it sort of look decent. And it starts to have a few issues with just keeping that number of points on the screen because actually it's rotating, so it needs to know where all these trace points are, and it starts to have a headache. Now, I've said before, Geogebra is not the best way to do arcane 3D plots. It's certainly not efficient, but because of the interactivity, you learn a lot while doing it. So then, having realized what's going on here, go and code it in some proper coding environment. But you can see that the structure is emerging, even if at one point it got to the end and it just gave up. It just stopped rotating and just said I had enough. Took about 20 minutes of real time just getting it there before it gave up. Hey, but at least we tried. I think to finish this story, I want to point out that it was through building the file to model something I already knew that I learned more about what I already knew. And that's one of the reasons I love talking about Geogebra. Or in fact, doing anything sort of creative alongside mathematics. When you're trying to actually build something from what you know, you do learn along the way. So now I've got a functional play thing, right? So I could crank this up to have 6 points. Let's get some sort of hexagonal. 6 points are over here. And I could put those points anywhere I like. Maybe I could go to an isometric grid again, but I'm going to leave it slightly skewed and not symmetrical. And I know that if I set a proportion, I've got a calculation for the fractal dimension of what I'm going. So maybe if I keep it nice and low, I know that I'm not going to need some sort of high dimensional viewer to make sense of it. So when it was 2-dimensional fractal dimension, I needed 3D to make sense of it. So I'm going to make the proportion, make it quite low. Let's keep the fractal dimension about 1.5-ish. I don't know what's going to happen here. I'm going to set the starting point to be on one of the points, and that stops any sort of like flyaway points. And let's think about what's going to happen here. I genuinely don't know what's going to happen. I'm going to create this shape, some design within that shape that gets scaled to each of these points at a proportion of about 0.31, the size of it, 31% around these points. But that's all I really know. Let's let it do it. And I like the fact that once we've kind of generalized here with the n and the proportion, we can use it as a sort of artistic playground. We can paint some fractals. We know the property of the fractal. It has a fractional dimension of 1.53, and we can just see what happens. I don't think this is going to particularly be a special one. Special artistic things usually come about from a decision to constrain things. So actually, when you put things in a square and constrain it to be a third, you get the Sierpinski carpet, and that is a neat one. But maybe I should have set these out in a hexagon to get some sort of nice hexagonal thing going on. Hey, build your own, knock yourself out, go and explore fractals with a certain fractal dimension that you know, because you can build the thing, and then go and code it in something else to be more efficient about seeing these outcomes. I'm going to stop wittering on now. I've enjoyed talking about this one. I'll enjoy talking about other constructions, but I hope you've enjoyed it as well, and maybe I'll see you next time.